Black holes obey the exact same laws as your cup of coffee cooling on the table. I'm not kidding. There are 4 laws of thermodynamics, the ones that govern every engine, every refrigerator, every living cell in your body, and black holes follow every single one of them. Not approximately. Exactly. And when we figured out Dewey-Hy, it cracked open the deepest mystery in physics, the connection between gravity and quantum mechanics. Let me tell you the story of how a brilliant young student named Jacob Bekenstein came to me and my colleagues with an idea so radical that Stephen Hawking himself tried to prove him wrong and ended up proving him right. All right, let me set the scene. It's the early 1970s. I'm at Stanford, still a relatively young professor, still riding the high of the string theory discovery from a few years earlier. And the hot topic in physics, no pun intended, is black holes. Now, here's what everybody thought they knew about black holes back then. A black hole is a region of space-time where gravity is so strong that nothing can escape. Not light, not matter, nothing. You cross the event horizon, that invisible boundary, and you're gone. Done, no coming back. And because nothing comes out, a black hole has no temperature. It's the coldest thing in the universe. Absolute zero. That was the conventional wisdom. And it made perfect sense. Think about it from a plumber's perspective. If you've got a pipe that only lets water in but never lets it out, there's no flow, no exchange. The pipe is dead. That's what we thought black holes were. Dead ends. Now, there was this young graduate student at Princeton named Jacob Bekenstein. Jacob was working with John Wheeler, the guy who coined the term black hole in the first place. And Jacob had this idea that made everyone uncomfortable. He said black holes have entropy. Let me tell you, when I first heard this, I didn't know what to make of it. Entropy is one of those words that gets thrown around a lot, but let me tell you what it really means. Entropy is a measure of how much you don't know about a system. When you look at a cup of hot coffee, you can measure its temperature, its volume, but you can't track every single molecule bouncing around inside it. There are trillions upon trillions of different arrangements those molecules could be in that would all look like the same cup of coffee to you. The number of those hidden arrangements, that's what entropy counts. The more ways the insides can be rearranged without you noticing, the higher the entropy. And Jacob was saying black holes have this property, not as an analogy, for real. The entropy of a black hole is proportional to the area of its event horizon, not the volume, the area, the surface. Now, that's a weird claim. In everyday physics, entropy is proportional to volume. You've got a box of gas, bigger box, more entropy. That makes sense. But Jacob was saying for black holes, it's the surface area that matters. And the reason was simple but profound. Everything that falls into a black hole gets smeared across the horizon. All the information about what fell in, whether it was a star or a piano or your grandmother's recipe book, gets encoded on the surface. Okay, so let me back up and explain why Bekenstein's idea was such a big deal and why it made a lot of very smart people very nervous. In the 1960s, physicists had been working out the properties of black holes using Einstein's general relativity. And they discovered some remarkable things. Roger Penrose showed that when a black hole forms, its event horizon area always increases. You can throw matter in, you can merge 2 black holes together. The total area of the horizons never goes down. Never. Stephen Hawking proved this rigorously. It's called Hawking's area theorem, and he was quite proud of it. And when you hear something that always increases and never decreases, what does that remind you of? Entropy. The second law of thermodynamics says entropy of a closed system never decreases. And here's the area of a black hole horizon, also never decreasing. That's a suspicious coincidence, but it goes deeper than that. In 1973, Jim Bardeen, Brandon Carter, and Stephen Hawking wrote a landmark paper, The 4 Laws of Black Hole Mechanics. And what they showed was astonishing. They showed that black holes don't just obey O&E law that looks like thermodynamics. They obey AL fo UR. Let me walk you through this because it's one of the most beautiful things in all of physics. The 0th law of thermodynamics says, if a system is in equilibrium, it has a uniform temperature everywhere. You leave your coffee long enough, every part of it reaches the same temperature. For black holes, there's a quantity called surface gravity. It's a measure of the gravitational pull you feel at the event horizon. And Bardeen, Carter, and Hawking proved that for a stationary black hole, the surface gravity is the same everywhere on the horizon. Uniform just like temperature. The first law of thermodynamics is about energy conservation. When you add heat to a system, its energy increases and its entropy changes in a specific, calculable way. There's a precise relationship between changes in energy, temperature, and entropy. For black holes, there's an exactly analogous relationship. When you change the mass of a black hole, which is its energy, there's a precise formula relating that change to changes in the horizon area, the angular momentum, and the electric charge. It's structurally identical to the first law. The second law, the one everyone knows, says entropy never decreases. For black holes, area never decreases. Hawking's area theorem, exactly analogous. And even the third law has a counterpart. The third law of thermodynamics says you can never cool a system down to absolute zero temperature in a finite number of steps. For black holes, you can never reduce the surface gravity to zero in a finite number of operations. A black hole with zero surface gravity would be what we call an extremal black hole, maximally charged or maximally spinning, and the laws of physics conspire to prevent you from ever quite getting there. For 4. Every law of thermodynamics has a black hole analog, and not just vaguely, the mathematical structure is identical. Temperature maps to surface gravity. Entropy maps to horizon area. Energy maps to mass. The whole framework transfers over perfectly. But here's the thing, and this is what made it so controversial. When Bardeen, Carter, and Hawking wrote that paper, they insisted it was just an analogy. They said, look, this is a mathematical coincidence. Black holes don't acetally have temperature. They don't acetally have entropy. Because if they did, they'd have to radiate energy. They'd have to glow. And everybody knew black holes don't emit anything. That's the whole point of a black hole. Stephen, in particular, was adamant about this. He said, and I'm paraphrasing, Bekenstein's suggestion that black holes have real entropy is nonsense. If they had real thermodynamic temperature, they'd have to radiate, and they don't. Here's the irony. Stephen set out to prove Bekenstein wrong, and in doing so, he proved Bekenstein right. That's one of the greatest twists in the history of physics. Now, this is where the story gets really interesting. Let me tell you what happened. In 1974, Stephen was doing a calculation. He was trying to show definitively that black holes have zero temperature and that Bekenstein's entropy idea was just a formal analogy with no physical content. So he applied quantum field theory to the curved space-time around a black hole. It was a technically demanding calculation. Stephen was brilliant at this kind of thing, and what he found shocked him. He found that black holes radiate. They emit particles. Thermal radiation with a precise temperature that depends on the mass of the black hole. It's now called Hawking radiation, and it's one of the most important discoveries in theoretical physics in the 20th century. Let me explain what Hawking radiation is, because it's genuinely mind-blowing. Think of it this way. In quantum mechanics, the vacuum, empty space, isn't really empty. It's seething with activity. Pairs of particles and antiparticles are constantly popping into existence and then annihilating each other so fast that you can't normally observe them. They're called virtual particles, and they're everywhere all the time. Now, near the event horizon of a black hole, something special happens. A pair of virtual particles pops into existence right at the edge. One of them falls into the black hole, and the other escapes. The one that escapes carries away energy, real energy, and the one that falls ineffectively carries negative energy. So the black hole loses a tiny bit of mass with each escaped particle. Here's the wild part. The radiation that comes out is THR-ML. It has a perfect blackbody spectrum, exactly like the radiation from any hot object. The coffee mug on your desk, the sun, a hot coal in a fireplace, they all radiate with a specific temperature. And so does a black hole. The temperature is inversely proportional to the mass. Big black holes are barely warm. The supermassive black hole at the center of our galaxy has a temperature that's a tiny fraction of a degree above absolute zero. But small black holes can be scorching hot, and here's the punchline. Once Stephen calculated the temperature, the first law of black hole mechanics, which was just an analogy, immediately told you the entropy. And it was EXACTLY what Bekenstein had predicted. The entropy is 1/4 of the horizon area measured in Planck units, 1/4 of the area, not the volume, the area. Think about how strange that is. Let me give you an analogy that I use with my students. Imagine you have a room full of furniture, chairs, tables, bookshelves. Now, normally, if you want to know how much stuff can fit in the room, you'd measure the volume. Bigger room, more stuff. That's what entropy is for normal matter. It scales with volume. But for a black hole, the entropy scales with the area of the walls. It's as if all the information about every piece of furniture in the room is painted on the walls, and the room itself is just a projection of what's on the surface. Everything inside is encoded on the boundary. Now, I want you to understand the significance of this. This isn't just a nice mathematical result. This is telling us something incredibly deep about the nature of reality. When Bekenstein first proposed that black hole entropy scales with area, he was ahead of his time. He was saying, without fully realizing it, that a black hole is fundamentally a TWO, dimensional object, not a three-dimensional one. All the information, all the degrees of freedom, all the entropy lives on the two-dimensional horizon. And this is exactly what led me to the holographic principle a few years later. I was sitting in my Stanford office, staring at the Bekenstein-Hawking formula, and it hit me: if the maximum information in any region of space is determined by the area of the boundary, not the volume, then maybe the whole universe works this way. Three-dimensional space is a kind of holographic projection of two-dimensional information. Maybe the room you're sitting in right now, with all its furniture and air molecules and everything else, maybe all of that is really encoded on a distant two-dimensional surface, and the three dimensions you experience are just the hologram playing out. I know, it sounds completely crazy, and when I first proposed it in 1994, half the physics community thought I'd lost my mind. But the math is solid, and it all started with Bekenstein and the four laws. Here's another thing I want you to appreciate. The Bekenstein-Hawking entropy formula involves all three of the fundamental constants in physics. It involves Newton's gravitational constant G, that's gravity. It involves Planck's constant, that's quantum mechanics. And it involves the speed of light, that's relativity. All three pillars of modern physics come together in this one formula. That's never happened before for any other quantity in physics. It's as if nature is telling us, hey, if you want to understand me at the deepest level, you need to figure out where gravity, quantum mechanics, and relativity all meet. And this formula is your Rosetta Stone. That's why we physicists get so excited about black hole thermodynamics. It's not just about black holes. It's a signpost pointing toward the unified theory of everything. So how did the physics community react to all of this? Well, it was complicated, and I want to give you the full picture because it's a fascinating story of how science actually works. First, Bekenstein. When Jacob first published his entropy idea in 1972 and 1973, the reception was mixed. John Wheeler, his advisor, was supportive. Wheeler loved big ideas, but a lot of other people were skeptical. The main objection was, if black holes have entropy, they must have temperature. If they have temperature, they must radiate. And everybody knew that black holes can't radiate. Stephen was one of the most vocal skeptics. He wrote a paper in 1973, the Bardeen-Carter-Hawking paper on the four laws, that explicitly said the analogy between horizon area and entropy is formal, not physical. He was essentially saying, nice idea, Bekenstein, but you're wrong. And then, in one of the great ironies of physics, Stephen's own calculation proved Bekenstein right. When he discovered Hawking radiation in 1974, he initially couldn't believe his own result. He rechecked the calculation multiple times. But the answer kept coming back the same. Black holes radiate, they have a real temperature, and therefore Bekenstein's entropy is real. To Stephen's great credit, he accepted the result and ran with it. He didn't try to bury it because it contradicted his earlier position. He embraced it. That's the mark of a great physicist. You follow the math even when it tells you something you don't want to hear. But the implications were enormous, and they set off a chain of events that consumed the next 30 years of my life. Because here's the problem that Hawking radiation creates. If a black hole radiates, it loses mass. As it loses mass, it gets hotter. As it gets hotter, it radiates faster. This is a runaway process. Eventually, the black hole evaporates completely. It disappears. Gone. So what happened to all the information that fell in? If I throw an encyclopedia into a black hole, and the black hole eventually evaporates into thermal radiation, random, featureless heat, where did the information in the encyclopedia go? Thermal radiation is random. It doesn't encode any specific information. It would be like burning a library and trying to reconstruct the books from the smoke. Stephen said the information is destroyed. Gone forever. That was his position for 28 years. I said that's impossible. It would violate quantum mechanics. Quantum mechanics says information is NEVR destroyed. It can be scrambled, rearranged, made incredibly difficult to decode, but it can never truly disappear. And that disagreement launched the black hole war. But I've told that story in another video. The point I want to make here is that EVY time G, the information paradox, the holographic principal complementarity, EAPR, quantum error correction in gravity, all of it traces back to those 4 laws of black hole thermodynamics. Bekenstein's entropy, Hawking's temperature, the realization that black holes are not dead, cold objects, but hot, dynamic, thermodynamic systems with a secret inner life. Let me also give credit where it's due. Andrew Strominger and Kamran Vafa in 1996 did something extraordinary. They took a specific kind of black hole, a supersymmetric one in string theory, and they actually counted the microscopic states. They calculated the entropy from first principles using D-branes and string duality, and the answer they got matched the Bekenstein-Hawking formula exactly. This was a triumph for string theory because it showed that string theory can explain where the entropy comes from. It's not just a formula. There are actual microscopic degrees of freedom that the formula is counting. I remember when Strominger presented that result at a conference, the room was electric. We'd been waiting for someone to derive the entropy microscopically for over 20 years. And there it was, perfect agreement with Bekenstein-Hawking. That was a very good day for physics. All right, so where does all of this lead? Let me tell you where my own thinking has gone and what the frontier looks like today. The 4 laws of black hole thermodynamics open 3 enormous research programs that are still active today. The first is the information paradox and everything connected to it. If black holes are thermodynamic objects with real entropy, and if they evaporate, then we must explain how information gets out. That's what my work on black hole complementarity was about. That's what the ER-EPR conjecture with the Juan Maldacena was about. That's what the whole firewall debate was about. The thread runs directly from Bekenstein's entropy to the deepest unsolved problems in quantum gravity. The second is the holographic principle. If entropy scales with area instead of volume, then the number of degrees of freedom in any region of space is 2-dimensional, not 3-dimensional. That's a staggering statement about the nature of reality. My 1994 paper, The World as a Hologram, was a direct outgrowth of the Bekenstein-Hawking entropy formula. And 3 years later, Juan Maldacena made this precise with the ADS-CFT correspondence, which gave us a concrete mathematical example of a holographic universe. That discovery transformed theoretical physics. The third program, and this is what keeps me up at night these days, is the question of quantum complexity. With Adam Brown and others, I showed that after a black hole reaches thermal equilibrium, its entropy stops growing. The 4 laws of thermodynamics say it's in equilibrium. But something is still changing inside. The quantum state of the black hole keeps getting more complex, more scrambled, harder to decode. This led to our complexity equals action conjecture and the idea that computational complexity might be the missing piece that tells us what happens inside old black holes long after they've settled down. And now there's the biggest unsolved problem of them all, de Sitter holography. Our universe isn't anti-de Sitter. It's de Sitter, expanding with a cosmological horizon. And the thermodynamics of that cosmological horizon, the fact that it has a temperature, the fact that it has entropy is telling us something about the quantum nature of the cosmos. But we don't yet know what. I've been working on this with Edgar Shagolian, Adil Rahman, and others. We've shown that there are serious obstacles to constructing a holographic theory for de Sitter space. My own no-go theorem with Gohir and Clubin proved that you can't have both perfect de Sitter symmetry and finite entropy. But I believe the answer is out there. The same Bekenstein-Hawking formula that started it all for black holes. Entropy equals 1, quarter the area, applies to cosmological horizons too. The universe has a temperature. The universe has entropy. And somehow the 4 laws still hold. After more than 50 years of doing physics, here's what I've come to believe. The 4 laws of black hole thermodynamics are not just a set of rules about exotic astrophysical objects. They are a one-iron bow. A window into the deepest layer of reality, where gravity and quantum mechanics become the same thing. Think about it. Thermodynamics, the science of heat engines and refrigerators and cups of coffee, was developed in the 19th century to build better steam engines. Nobody doing thermodynamics in 1850 imagined it would tell us something about the quantum nature of space-time. But it does. The same laws that tell you why your coffee cools down also tell you that black holes have entropy, that information is preserved, that the universe might be a hologram. I find that beautiful. The universe doesn't have separate rules for different things. There's one set of rules and it works everywhere. In your kitchen, at the event horizon of a black hole, at the boundary of the observable cosmos. Jacob Bekenstein, who started this whole revolution, passed away in 2015. He never won the Nobel Prize for his discovery, which is a tragedy. If you ask me, the Bekenstein-Hawking entropy formula is one of the most important equations in all of physics. It's our best clue to quantum gravity. And every time I write it down, I think of that brilliant young student who had the courage to say something nobody else dared to say. I'm 86 years old now. I've spent half a century chasing the implications of those 4 laws, and I'm not done yet. Because the 4 laws aren't just about black holes anymore. They're about the universe itself. And the universe still has secrets it hasn't told us.